of the other object. So the Earth has a gravitational force acting on me. I'm close enough to the surface of the Earth that it counts as weight. That weight vector is pointing towards the center of mass of the Earth, which we assume is the center, close enough to the center of the Earth. Meanwhile, I'm pulling up on the Earth, and that force that's acting up on the Earth is pointing towards my center of mass, which is somewhere around here.
Is the center of mass effectively the median?
Not, sort of a weighted average.
Okay.
What does it say under the friction? It says the most desired.
Here,
No, under the Wickman's methodology.
Desired relative motion, yeah. It just looks like.
yes.
Okay, so this isn't really like for class, but do you know with like gravitational anomalies, would that still be the case?
What kind of gravitational anomalies are you considering?
I know there's a name, but I don't know the name.
All right, so in terms of gravitational force, you could get into a question of, is there a gravitational force really pulling things together, or does one of the objects warp space so that the other object, it would just naturally travel towards it?
Like an astronomical scale.
Yeah,
thing.
I mean, that part of Einstein's theory of relativity is that mass actually warps space and time. And so,
It does. It's a law.
okay. But in terms of classical physics, this will hold us, unless you want to get into the really obscure stuff, which the general relativity kicked my butt. So at some point, I'll go into a 5-minute version of it, and I will leave the math out.
Can you remind me what you said about center of mass being basically some kind of average?
Weighted average.
Weighted average.
All right, I can feel the excitement. People are pumped. Be ready to do a force diagram and actually see some of this stuff in action.
Yes.
Okay, on the board, not necessarily in action. I assume that was raise the roof, is that?
Yeah.
All right, as we go on our journey here, the first one is box falling. Put an exclamation point because it's that exciting.
Yeah.
Not as exciting as box on ground or box on ground, but it's out there. All right, so first thing I'm gonna do is I'm gonna draw what's going on. So I have the ground here, and when I remember, I'll put the little hash marks. The hash marks are an indication of something that is not moving. So from our point of view, we're just looking at a box that's falling. We're not worried about the Earth rotating or anything like that. We got basically flat Earth. We'll get
So what
into
would
Earth
indicate
rotating
it's
in
moving?
chapter 6.
What would indicate it's moving? Is there a special symbol for that, or just no lines?
Probably for Earth moving, I would draw Earth.
Okay, that makes sense.
All right, and I have a box that is falling. Now, we are ignoring air resistance. Notice air resistance is not over there because that gets very complicated very quickly. And even to do the simplified version, you need calculus, so we will avoid air resistance.
Are we allowed to use our calculators?
Sure,
Thank you.
you won't need it for this.
Oh, okay, no.
So, but I'm putting little streams here to somehow indicate that it's falling, not that it stinks. But I'm not worried about air. There's just I need some sort of indication that it's falling. The next step is I now need room to work. Now in this particular example, I have plenty of room to draw all the areas that I need to, but what I'm gonna do instead, just from a matter of process, is I'm gonna draw my box over here, and I'm gonna draw my ground. So this is where I'm gonna do my work. That's the picture of the problem. This is my workspace. I put up my checklist. And I first asked myself, are there any of these forces that we can immediately eliminate that we know they are not involved?
Friction,
Why not?
because there's no contact.
All right. What else? Why not
We
tension?
have gravitational force.
Because, there's no like rope or chain.
All right.
Alright, it's not taught. In any case.
Yeah, there's no rope chain or anything like that. All right.
Normal,
Why not normal?
because there's no contact.
All right. Normal's gone.
Other,
Why?
because there's no unknown force.
Yeah, I didn't specify any additional force. There's no hand of God or anything like that.
Yeah. That's exactly what
And we all know hand of God is reserved for Maradona's fake gold back in the World Cup. Anyway.
Can you,
All right,
can
so
you
we're left
remind
with
me,
gravitational force.
can you remind me why O isn't involved?
Because I didn't state as part of the problem that there was any additional force with an unknown source
No Philip, okay.
or irrelevant source. I have two masses here. I have a planet, I have a box. It's near the planet. And so since it is near the planet, it is a weight. And so it is pulling down. So the ground is pulling down on the box. Now think about the wording I just used there. I said it's pulling down on the box. That's exactly how I'm going to draw my arrow. I'm going to draw it down on the box. And I'll put a little W there to indicate that it is the weight. They come in pairs, and so if the ground is pulling down on the box must be pulling up on the ground. And there we have our first force diagram. That's right, it is a cause for celebration. All right, rookie mistakes. Rookie mistake number one. The number one rookie mistake changes from semester to semester. I haven't codified it completely. No man's land. I've had this way too many times. I look at that and I'm going, I have no idea which arrow is acting on which object.
So you have to draw in the object.
There needs to be some sort of indication. Now, if this had been drawn like that, yeah, I know what's going on there. I can take a pretty good decent guess that that goes with this and this
But
goes
if
with
they're
that.
side by side, then it just looks like friction.
Yeah, this is just wrong on several levels. Rookie mistake
So,
number two.
can I try something?
Yep.
If I were to draw it. Okay. Like that, it would make sense?
Yes.
Okay.
Yep. Just so long as it stops, because I have seen it drawn all the way. Which again, is pretty much the same as no man's land. There we go. All right, rookie mistake number two. Backwards.
That's normal.
If they were touching, it would be normal force. Yeah,
So what is it?
it's wrong.
There's no force acting on it, on each other in this case?
There are. The mistake is, this is rookie mistake. The mistake is also all forces have a source and a receiver, and they draw the force on the source and not the receiver.
Okay,
They know that the box is pulling up on the ground, and so they'll draw an up arrow on the box, not on the ground.
Okay.
It just looks like they're repelling each other now instead of
Yes.
attracting.
And that's probably it for rookie mistakes for now. The next one we'll have a couple more. Cringing inside because the number of times I've seen it. Okay, mistakes, don't do these. Thus the mystery next statement. Questions before we do box on ground? All right, here we go. First thing, I'm gonna draw the picture of what's going on. I have the ground. I have a box. It's on the ground. Now I've drawn a picture of that. I now need to draw my objects so that they are, so I have room to do work. I put some space in between them because I need room to draw my arrows. I am not claiming that the box is in the air. All I'm doing is I've drawn a box, I've drawn the ground. Technically, you don't have to draw them in that orientation, but I recommend it.
To avoid confusion.
Yes.
Okay.
Go to our checklist. Now, if you'll notice on this, well, first off, what can we eliminate?
Other. Tension.
Or something over there?
I don't see any tension either.
I don't think
Is that what you said? Tension?
Yeah, I don't think there's friction either if you're gonna specify a desired motion.
Yeah. So if it looks like I've drawn level ground, or I intended to draw level ground, then assume that it is. If in doubt, ask. But I'm not gonna play a game where it's a 1 degree angle and say, I can't believe you missed that 1 degree angle. No, not doing that game. If it looks like I intended it to be level, it probably is supposed to be level.
And then gravitational.
What?
We're getting rid of it?
Yeah.
Why?
Well, I'm not sure,
Box
but,
still being pulled to the surface.
but, okay.
Well,
Yeah,
if there
that
were
makes
no
sense.
gravity, then it would just be like, woo!
Yeah, it would go around, but I'm just wondering, so, if the two masses were in contact or like right next to each other, it can still be gravitational?
Yeah, as long as there's contact is irrelevant to the gravitational pull.
Oh, okay.
All right, so we have these two forces involved. Let's start out with, personally, I think the gravitational force is the easiest one.
Hold up, why is F gone? There is contact.
There's no friction though.
But is
There's no desired relative motion.
Oh, right.
If the ground were frictionless, that box is still not sliding one way or the other.
Yeah, it's not going sideways.
Gravitational forces. Which way is the gravitational force acting on the box? Matter of fact, the direction of the gravitational force acting on the smaller object defines down. All right, they come in pairs, so where's the other part of that pair?
Ground.
All right. Done. Normal force. Normal force is a force preventing one object from going through another. Right now, I have a normal force acting on me from the ground. I assume I'm not falling through, and I don't have magical powers to levitate.
So you're not quantum phasing, okay.
Right. As I lean on the desk here, I have a normal force pushing up on me from the ground. I also have a normal force pushing, it depends on how you want to do it, but somewhere there's a normal force pushing on me from the table as well, because I'm not going through it. Box is not going through the ground, so something's got to be keeping it from falling, because I got this gravitational force acting on it.
Yeah.
That's the normal force. Some textbooks, and I don't think yours does this, but some textbooks will call it a support force. That I think is limiting for some of the examples that we will do later. But which way is the normal force acting on the box? If it's pulling up, that means there's some object above it. It's not pulling down because then nothing's holding it up.
To the side.
The issue before was the word pulling. It's not pulling up,
Oh, it's pushing up.
pushing up.
Oh, yeah.
And what's the other part of that pair?
Pushing down.
If you're standing outside and then you step away and you look behind and you see you left footprints, that's the force that leaves footprints.
So
Yes.
where does the perpendicular direction come into play?
The surfaces of contact, the surfaces are here, so it's perpendicular to that.
Okay.
Imagine the box is at like, it starts at 0, 0 and it ends at 1, 1. Ta-da.
So we just don't draw that then unless specifically asked.
Right, well, the fact that it's labeled as a normal force, and somehow I lost the body of the arrow there. Try to draw it as perpendicular as you can, in terms of drawing.
Where do we put
I think I
gravitational
started that
force
sentence
in
in one
this?
direction and then changed halfway through it.
Yes, you did.
What was your question again?
Yeah, weight is. Let's say gravitational force, weight.
Or concern?
Different answer, the same thing.
Are we supposed to draw the perpendicular part of it?
Oh, you mean the actual symbol for perpendicular?
I guess then with the arrows.
Yeah. Are you asking if you need to draw this thing?
Yeah,
No, you don't have to.
okay.
All right, questions to hear? I do want to point out that if I drop this box and it hit the ground, box on ground takes into account whether it's been sitting there for a while or whether it just made impact. The force diagram doesn't change. If I'm jumping off the ground or just standing here, that's the force diagram. What the difference is in terms of analysis is, are these equal to each other in magnitude, or is one bigger than the other? That will affect what's gonna happen next.
So if they're different, do you draw one like y sub bigger or something?
If the normal force is bigger, then technically you would draw y as a larger force.
So you just draw a big y?
If y is bigger, I'd have y going like that, and then maybe weight like that.
Oh, so the arrow is longer, okay.
Yeah, arrow's longer. Yeah, not the symbol.
Thicker or something.
Because what we're doing is we're not setting up for doing graphical addition. We're setting up for later analysis, and so all I need is just the direction of the arrow and the symbol. I don't have to worry about the size of the arrows at this point. I don't have to worry
So
about
if
the size
y1
of the
doesn't
arrows.
equal y2, then you show the difference with the arrows. Did that make sense?
I missed it because I was
If
saying something.
y1, it gave
If there's two normal forces,
if force 1 and force 2 are not equal, then you show the difference in the length of the arrows. Can I write that as y1 does not equal y2?
the trouble is, without more information, which one would you draw longer than the other?
Should I just put y sub bigger?
No y greater than.
Or we're using different, I have different letters symbolizing them, representing them. There's nothing in the problem that indicates why.
So y is not equal to w, okay.
We don't know. At this point, we don't know. Let's take a look at the full process, what we're doing here. What I refer to as the facades method. This is the full analysis that we will be doing, well, actually for quite a while, but this are the steps. First thing you do is the force diagram, which is what we're going through right now. Next thing is we determine the direction of acceleration, and for that, we need more information about the problem. Acceleration, direction. CA stands for coordinate axes. So once we figure out the direction of acceleration, we establish our coordinate system. And it's at that point that choosing everything to be left, right, up, down, it does not necessarily make mathematical sense. D is for decomposition. E, equations of motion. And I will say it more than once probably. When we talk about equations of motion, we are not talking about the equations from chapters 2 and 3. Equations of motion are a reference to F equals ma. The first S is for substitution. The second S is for solving. Right now, we are concentrating on that one piece right there. Are we ready for box on ground?
As long as you don't erase that. And this is a process, like PEMDAS kind of process, you go through?
Yeah.
Okay.
All right.
Yes.
Now, if you're trying to picture what's going on here, there's the ground with a box on it,
And another box.
and another box on top of that. Just in case that still was not enough, let's draw the picture, because that really should be the first thing we do anyway. I'll call that box A and box B. If you wish to give them the other names, Fred, Evan, that's fine too. Lucy and Ricky. Alex and Ralph. Anyway. So, to do the force diagram, first I need to separate the objects.